Hello, everybody. This is a review for Chapter 4, topics in Chapter 4 for ISIS 565. Excuse me. This is the topic of network management, and the way this is split up is we have two parts to this. So there is the part about TCP as best effort service, the concept of quality of service, and the role played by service level agreements. So this is sort of one part. And then the second part has to do with the simple network management protocol and how SNMP, as implemented through some of these software projects here, can help you in addressing some of the concepts and problems that pop up in the space of quality of service. So let me begin with TCP as best effort service as a concept. There we go. As a TCP as best effort service, it's more of a concept, as this little article on Wikipedia tells you. They are comparing it to the postal service, right? So right here, let me increase the font size here. It's easier to read. The postal service, and then how it delivers letters and so on. So the idea here is that the postal service will deliver your letters using a best effort approach. They don't schedule things in advance unless you buy the different services like next day or global priority and so on. But for a regular letter that you mail, they try to deliver it. If you're not there, you may get it the next day and so on. And so the idea is that the post office, depending on how busy or free they are, will try to deliver the letter, and eventually it'll get there. And so the idea here is that when we look at TCP, which is designed to provide some kind of a guarantee of delivery, as in, the data will eventually get there. If the data doesn't get there, we'll try to retransmit repeatedly until the data gets there. So TCP is trying to give you some kind of a guarantee of delivery. What it cannot do is give you a guarantee of delivery based on time. So for instance, you can either get the guarantee of delivery, or you can get timely delivery without the guarantees. So in fact, down here it talks about that, and it talks about the example of UDP, which we've looked at before briefly, which is a way where data is sent across. There are only some very basic error checks, but retransmissions are not part of UDP. So the data gets there. It may be missing bits and pieces here and there, and so be it. So this is good for audio and video. For instance, if you're doing a phone call, or if you're streaming video, there may be a little drop in quality. Some parts of the audio may not be quite audible, but that's acceptable because UDP delivers things fast, right? So think of it as a balance between, do we want things to be delivered on a guarantee, or do we want things to be delivered on time? And so the the balance is between the timely delivery and delivering the entire set, as in all the packets. And so that's sort of the best effort concept, and this is inherent. This is a part of TCP. This is how TCP works. It is by design, and the reason for that is that the internet around the world is something that runs on a whole bunch of different devices. Each owner of the network is responsible for his or her network and the devices on it. So for instance, at home I may have a UVerse access point, and I may have a D-Link switch or something like that, which are consumer grade, okay kind of quality. They're not very good. Whereas at work, we may have a Cisco router, or we may have switches from Juniper Networks and so on, which are enterprise grade and very good quality. So the quality of these devices will vary, the capabilities of these devices will vary across the world. And in an effort to accommodate everybody, so that we can accommodate the really slow ones and the really fast ones, we basically come up with this whole concept of TCP, where TCP is forgiving and it redelivers and all of that stuff. But in that effort to be inclusive of all of those different scenarios, the one thing that suffers is a timely guarantee, that is, guarantee of delivery with respect to time. Excuse me, I'm dealing with some allergies, so pardon the sniffling. Now, once we switch over from that concept of timely delivery of what TCP does and how it works, we switch over to the concept of quality of service. And the way this comes into play is that with quality of service, and quality of service is a concept that's applied to networks, but before we get into QoS, here's the dilemma. So businesses as we know it offer services where they require timely delivery of products and services. So you buy a pair of shoes and you want it the next day. Amazon, for instance, will have to guarantee that. And so a lot of the businesses have to guarantee timely delivery. However, the business processes are running on top of software that runs on top of TCP IP, which by itself does not provide guarantees of timely delivery. So the dilemma here is that we run businesses that provide certain or work with certain goals. However, those goals cannot be fulfilled by the technology platform, which in this case is TCP and IP. And so to fill that gap, we've come up with quality of service. So quality of service is a general concept applied to networks. Here it says it's applied to telephony or computer networks, but in our case we are just interested in computer networks. And the idea here is that what we want is we want some kind of a guarantee. So we want the service to run in such a way excuse me, where let's say I want to set up a call between here and Singapore, and I don't want any packets to drop, and I don't want any congestion, and I want the stuff to work smoothly. What I would have to do is I would have to pay extra to my ISP and say that please reserve the connection between here and Singapore. So what they will have to do is they will have to pay extra to make sure that that particular connection that I have from here to Singapore over all the different hops over the internet are in fact reserved. And they will have to do things like right here it says over provisioning, which is you figure out your peak traffic load and then you account for extra resources so that there is no congestion. And so since there is no congestion, you don't need to worry about anything getting stuck. Additionally, in this case, they'll have to use a protocol. There are several, like for instance, there is one called RSVP, which is a reservation protocol. And what they will do is that they will actually reserve the connection between here and Singapore for that phone call. So there are a whole bunch of different ways. Here's RSVP that I was talking about. Resource reservation protocol, RSVP. It's an internet standard. So you pay more, they do RSVP, they give you that guarantee, and the services work out. However, what happens is that we can do this on a case-by-case basis. We also cannot do things where we say, I'll just call you when I need it. So we sign contracts and we say, these are the requirements of the business, and we'd like for the contract to support that. And so right here says when the expense of mechanisms to provide QoS, quality of service, is justified, network customers and providers can enter into a contractual agreement termed as a service level agreement. So the service level agreement is talking about a certain level of service we require so that we are able to guarantee timely delivery of products and services for our business, which otherwise are not made available via TCP. So that's sort of the whole reason why we have quality of service in the middle and the service level agreement concept right over here. Yeah, Wikipedia has something up here. Well, facts matter. Yes, they do. Service level agreement is a contract, so typically you'll see a document that says, we guarantee so many megabits per second, and we guarantee that our equipment will not fail, and so on and so forth. And then the service level agreement relies on certain terminologies, like here, mean time between failures, or mean time to repair, mean time to recovery. So mean time between failure is to take data from equipment, let's say hard drives, and try to figure out that what is the average time between failure of drives. And that gives you, so this is something that comes from the vendor, say Western Digital or Seagate or whoever makes hard drives. And then that will give you an idea of what the MTBF, or mean time between failures, is. And then you can look at that and try to figure out whether you should over provision your hard drives by adding a second drive, a third drive, a fourth drive, and so on. Then you also have this thing called mean time to repair. This has to do with if something breaks, how long does it take to repair? How do you factor that into your operations? And then mean time to recovery is for systems where there is failure, but you don't need to repair, you basically need to recover. And then the biggest part here is, once you have all that stuff, you identify which party is responsible for paying the fees, the penalties. And so there has to be this agreement that comes beforehand with your service provider to be able to do this. Just as of yesterday, we had a failure where Amazon failed. Amazon S3 service failed. You'll see this all over the web. This is an article from The Verge. And basically what happened is that they have this service called S3, Simple Storage Service, that failed, and it failed evidently in many regions, but mostly Northern Virginia, as you can see here in the article. And all those little yellow and red items are telling you that it has failed. And in this case, what will happen is that any business that ran on Amazon's S3 for storage will now be able to penalize Amazon, and Amazon will have to pay the penalties because they failed. So effectively what happened was Amazon's SLA was in some sense violated because Amazon was not able to live up to its contract. So that's where SLAs come in, and there are several kinds. They're customer-based, service-based, multi-level, and so on, which I'm not going to go into in detail. There are many metrics that are used, like mean time to recovery, turnaround time, like in the tech support industry, they look at things like first call resolution, like percentage of incoming calls that can be resolved without the use of a callback. So a whole bunch of metrics that allow you to measure how the industry does, and then be able to apply the terms and conditions of that SLA to then penalize the provider. In this case, it happens to be Amazon. So that's sort of the part one of the story, which is we have TCP as an inherent technology, and there really isn't any major reason to change TCP at this point. It works well, and it does what it's supposed to do. So that's not really the problem. Businesses have changed. There used to be a time when you could, your business just ran 9 to 5 and you'd go home. And now we have businesses that run 24/7. And the expectations have gone up, which is we want our servers to be running 100% of the time without any downtime. So those are the things that have changed, which then brings into play the service level agreement. And of course, the quality of service is that technology platform that fills the gap of where TCP is not able to provide the guarantee. So that's what's happening with these three items here. Now, switching gears, let's look at, say, a company like Amazon that provides these services, storage and cloud and so on. So if you were Amazon, there are a couple things you'd want to worry about. One is you really don't want failure. So what happened here is not something you want to see. You don't want to see any yellow or red items here. because whenever this happens, you lose money. So it's not something you want, right? And if that's the case, you want to figure out strategies in which you can build your systems so that in case one device fails, there is a backup that kicks in. So typically, for instance, if you have a server, you have a hard drive, you would throw in a second hard drive to back it up. And so if the first hard drive starts to fail and shows signs of failure, you would switch over to the second. With hard drives, we have lots of standards. There's one called SMART. Let's see. So SMART is a self-monitoring analysis and reporting technology. It is built into hard drives now. You find these in both spinning drives and solid-state drives. And basically what it does is it collects a lot of very low-level mechanical data, and SMART is then able to report some of this back to the system. And so SMART will actually start to tell you when something is starting to fail. And so if you were running a server and you had two hard drives, the main hard drive, you would want to keep an eye on SMART, and then SMART would come back and say, okay, there's failure, let's switch over to the second drive. So we have systems like this, and so we need systems like this in the hard drive, we need it in the network card, we need it in the memory, we need it in all kinds of places. You also need systems that can detect temperature, because stuff fails miserably when it gets hot in the computing world. You need power spike measurements and a whole bunch of things. So imagine that everything is now being measured through sensors, and now you need a platform where all this can be collected and processed and then be managed. In fact, in some cases, managed preemptively and automatically. So SNMP is a protocol that allows us to do this for networks. SNMP stands for Simple Network Management Protocol. It's an application layer protocol, and it's been around for a long time. The way this works is that it's actually very simple. That's why it's called Simple Network Management Protocol. This picture here gives us a good idea. So basically what you have is you have a manager, the mothership here, that's running SNMP server, and it talks to a bunch of other agents using the get and the set request. So get request, set request, get response, set response. So if you send a get request, you get a get response. If you send a set request, you get a set response. And here is the agent in green on the right side. So most basic setups are, you have the manager, this SNMP server here, you have an agent, and that agent talks to a whole bunch of devices. So these things, agent 1, 2, 3, 4, 5, could be routers, switches, CPU temperature gauges, whatnot, and the agent is reporting. The one over here with agent 6 is a slightly different case. I'll get to that in a minute. So the way this works is the get request is used to get data from the agent. So the SNMP server will use the get request to get data from the agent, saying give me data on temperature, give me data on how many bits came into the network card, how many bits left the network card, give me data on read-write rates on the hard drive, give me data on SQL queries on the database, and so on and so forth. So you can see that it's a whole bunch of things. It's not just one or two things. And so get request has to be actually very simple, and the complexity is managed elsewhere. So get request, get response is to be able to get that data from the agent. Set request and set response is to actually make changes to devices on the other side through the agent. So if I want to, for instance, reboot an access point, I would use a set request to the agent and say, go ahead and start the process of a shutdown and restart. If I want to turn off a Wi-Fi access point, I would use a set request. If I want to block certain IP addresses, I could use a set request. So set request is to make changes, get request is to gain or get data. Now this is done on a very simple level. So all the get and set requests are simple. The complexity of the device on the other end, whether it's a router or a database server or a hard drive, is actually managed quite cleverly using this thing called MIB, Management Information Base. So MIB is a standard. It has a structure. It's like a hierarchy. And so the vendor that makes the device will then provide the data for that device through this MIB. So imagine that you bought a Cisco router and you wanted to get all the SNMP data from that Cisco router. Well, Cisco will provide you with the MIB, which is sort of like a database, and that MIB will have all the functionality of Cisco. So the MIB for a Cisco router, for instance, will be much larger than the MIB for a D-Link router, because D-Link routers are cheaper and smaller and less capable. So the complexity of the device is addressed through the MIB, and the process of getting that data is kept simple through the get and set request. This little corner case here of agent 6 is different. It uses something called a trap. So this is where the manager does not in fact initiate the request. So it's not like the manager is saying give me the data. They set up something called a trap on the agent 6 in this case, and the agent is then able to send data periodically. So this is very useful in cases where we don't know where agent 6 will be. It may be on the internet and may sort of come on and off intermittently. So we set it up so that whenever it is active, without asking, it will send us the data using SNMP. And so agent 6 in this case is set up using trap, as you can see here, trap, and then there's a trap receiver within the server that gathers the data. It's an interesting corner case, but not something to worry about. Main thing is to understand how the get and set requests work, and SNMP is able to do this. And of course, this is very simple because the complexity is in the MIB, and this is based on you can see here it says Management Information Base version 2. There's a standard for this. If I click on that, you'll see. Let me increase the font here. These are standards for how data is provided through the MIB, and so this is provided by the vendor of the device itself. Okay, so that's pretty much the basic stuff about SNMP. There's a lot of detail here that I'm not going to go into. Next comes we have the protocol, we have the devices that speak this language. We need software platforms that can implement all this. So I have 4 examples for you. Let's start off with Cacti. Cacti is an open source project. In fact, all the 4 there are open source. What Cacti does is it has an engine that speaks SNMP, so it gathers all the data. But Cacti adds a layer on top that allows us to actually graph things and look at it in a much better way. So there are some screenshots here which are probably easier to work with. Let's see. Let's look at a larger one. So here's one. This is web-based, as you can see here in the browser window. It shows up, and Cacti will automatically organize this based on some data about the location. So you can see this little tree structure here. So there's one for Dallas. These are the switches in Dallas, and here's each switch. This one is highlighted, and so you can see the data for that switch. So in this case, we are collecting SNMP data from a switch in Dallas that is coming in, and it then creates a nice little chart for you or graph for you here with the inbound traffic in green, outbound in blue, and there's a time scale. So this is midnight, 2 a.m., 4 a.m., all the way through 10, 12, 2 p.m., 4 p.m., 10 p.m., and so on. So this is the whole cycle across the day, and you can see where the peak traffic is. So peak traffic is 10 a.m. to 11 a.m. Then there's a little dip. My guess would be this is lunch, and then people come back, and then there's a dip again. Things slow down in the afternoon. Depending on what you eat, your afternoon can get slow. And then this is like, oh, let's get stuff done and go home, right? So it drops off there. So it's actually pretty interesting to be able to see all this data here, and then other levels of detail in this case. Let's pull up another one. This one here. So in this case, we are seeing again traffic. So this is traffic for a web server. Looks like it's coming from a K through 12, so that's a high school in Big Springs, PA. So that's from Pennsylvania, and you can see the traffic here. In this case, we are getting the CPU usage. So the processor, how much work it's doing for the user versus system. You can see week 28 to week 29 there was a spike. Whatever happened there. This is the load on the server, so you can see there was a spike there, then it was fairly down, and then it's been pretty steady after week 31. How many users were logged in? So this gives us data to a very fine level, such as CPU usage. You can even do things like how hot is the CPU, the actual temperature in centigrade, and so on. So this is Cacti. We actually use this at State. I've used this on my projects as well. Fairly easy to use, open source. You go to cacti.net and you can grab it from there. So this is basically visualizing SNMP data. Here's another one called Munin. This came out of Norway. I think originally the project was for a newspaper company, and then they made it open source. Let's make this slightly big as well. I've used this as well. In fact, we used this for the one laptop per child project. And they have a demo here, a live demo of development version. Let's see how that works. So this is a live version running, and you can pick one of those machines here. So on the left side, you can see their categories, if I wanted to see kernel level detail. So that's for that server, looking at kernel memory, how much memory is consumed by the kernel itself. And you can see it's pretty steady there. And this is by day. You can switch to by week, and you'll actually see some patterns here. So this was on the resolution of the hours of the day. This is the days of the week, and then this is the month. So you can see a zoomed out view. Again, you see little spikes there for every day, and then finally across the year. So these are all logs, right? These are all logs being collected on the system. We use SNMP to talk to the system and gather all this. Looks like there was a shutdown there and over there. You can do the same thing for disk usage. There, again by day, week, month, and year. So Munin is quite useful. We use it a lot for one laptop per child, and we are able to get some serious data. There is logins, so how many people logged in, how many failed passwords, that kind of stuff. And this is available at munin-monitoring.org, also open source software. So these are two that are widely used. If you want more reporting, there is one called Nagios that has been around for a very long time. I've used this in some other projects from, I'd say, maybe 10-12 years ago, so pre OLPC days, and these guys are still around. They've now switched over, they call it infrastructure monitoring, but basically it's the same thing. They also have an open source version that you can download somewhere on their site. It's usually view open source solutions there. So you look at open source. So this stuff is open source. The plugins, some of them are, some of them are not. Then there are tools for mobile, platforms and so on. Let's find a screenshot. Architecture. core documentation. It's always hard to find these things on these pages. Let me do a search. Here we go. So we found some. So here's a picture. Let's go find the page. Oh, not on Softpedia. I think there was a page here. Here we go. Screenshots. So this does a little bit more reporting, as in you can see not just your graphs, but oh, come on. Just okay. Not a great picture, but I hope you can, there we go, make out some of it. So this gives you sort of a dashboard at a glance. Here are all the machines. The green is okay, the yellow is there's a warning. It'll tell you what it is. It has also this is the actual log itself, unprocessed. This is that dashboard view. They also, I don't see it here, but they also had things where you can see it on a map. So it shows you geographical location and all that. So this is so Nagios is like Munin or Cacti, but gives you a little more in terms of reports. And then finally there is Xenos, which is also open source software, but there is a company behind it, as is the case with Nagios. And so these guys try to sell you services. So in most cases it's kind of hard to find their open source version. But it's there somewhere. Let's see. Oh, here. So they have a link called Community, which is the word for open source. And so here it is. You can download it from here. This is the open source version. So in fact, they have I don't know. This still sort of looks like, oh, here, core for open source users. Visit the community. It'll take us back to that page. From what I recall, these guys actually have versions also for VirtualBox and so on. So you can actually just grab a pre-baked version and run it directly on VirtualBox somewhere in here. I remember it took a while to go digging. Anyway, these are four examples of software platforms that implement SNMP, and by using platforms like these, you can keep an eye on your devices, and once they start to pop up as yellow or orange or red or any kind of warning, you know that that device is failing. You proactively then switch those out while the services are running, which would then result in no downtime for your customer, no penalties for you, and you're able to then guarantee a certain level of service to your customer. So that's sort of the whole set of logic for why we require all of these pieces of software and SNMP is to basically support a certain level of service because TCP is not able to guarantee that. So that in a nutshell is our topic for chapter 4, and hopefully that'll give you an idea of how all of it comes together.